Hello, I'm Perdita Stevens, and it's a great pleasure and honour to give this keynote talk at Lambda Days. It was also, I have to confess, something of a surprise to be asked, because I don't really think about myself as being a functional programmer, although I have written a fair few functional programs in my time. What I have done recently is to write this book, How to Write Good Programs, A Guide for Students. Now, this is a book which is aimed principally at first-year university students and students doing their first programming course in some higher education setting. And there's a little extract from the blurb on the left-hand side. The idea of the book is to try to teach explicitly the skills that we sometimes just assume that students will pick up as they go along, learning whatever programming language we decide to teach them. Skills like how to debug their program, how to test it, how to write clear code, and generally speaking how to get unstuck when they get stuck. And so I decided to include in this book examples in Python, Java and in Haskell. And incidentally, before I move on, of course it would be lovely if you would all buy this book and recommend it to your students, and there's a discount code down there which gets you 20% off at the CUP site, although it's still worth checking other online retailers in case you can get an even better deal. So in writing it, I had two main classes of aim. The one that's not on this slide is about which students it's aimed at. So one of the things that I feel passionately about is that it's really important to make sure that those students, and there are many of them, who at some point in their first programming course feel a bit lost and wonder whether they can get through it successfully, don't learn to identify themselves as people who can only ever aspire to being mediocre programmers. Because I feel that those students, I've seen many times over decades, those students go on to be absolutely excellent programmers later on. And so I wanted in one book to be trying to offer things that would hold people's hand a bit and help them get to the end of their first programming course successfully, and at the same time challenge people to develop good software engineering habits and think about what it is to be an excellent programmer and set off on that path. So that was one thing I was aiming at with this book. The other thing I very much wanted to do was to try to encourage people to learn skills and develop the metacognitive skills associated with them that will allow them to learn a thing not just in the setting of their first language, but also in such a way that they are able to go on and apply it to future languages that they learn. Of course, the ultimate reason for wanting to do this is this quote at the end from the book, that if you're at the beginning of your programming career, the language that you will use most in the end may not even have been invented yet. So if our learning at university is to be useful, it had better be transferable to future languages. But I've noticed that students very often don't transfer skills from one language to another. You might teach them to do unit testing in Java, and it might not even occur to them that they can also do unit testing in some other language that they learn later. In Edinburgh, we teach students Haskell in their first semester, and then we go on to teach them Java in their second semester. And quite a lot of places do that kind of thing. Incidentally, in the process of looking for things I would talk about today, I came across a lovely letter by Edgar Dijkstra protesting against a plan to replace Haskell in a first programming course at Texas by Java. And the nice thing about this letter is that it starts off talking about how it doesn't really matter that people learn this rather obscure language Haskell in their first programming course, because it won't be, for most students, their first programming course, programming language. They'll have learnt something else at high school, and this is good because it puts students on a level playing field and so on. And then he has 3 asterisks, and without a trace of knowledge of inconsistency, he goes on to argue that it's really important that you make a good choice of first programming language. So he's arguing for Haskell both on the basis that it isn't people's first programming language and on the basis that it must be people's first programming language. A lovely example of having your cake and eat it. But there you go, you can look that up if you like. I need to say a bit about why we care about writing good programs and about what that means. Well, we care because it is one of our major approaches to software engineering's wicked problem. So the main problem of software engineering, the reason why software engineering is hard, I claim, is that there is just too much information. There's too much information to fit in a human brain, so we need somehow mechanisms to control it all, and especially it changes too often, and so whatever our mechanisms for controlling it are, they have to handle the fact that it will repeatedly change. We cannot ever set it in stone. And in most talks I would now go on and I would talk about models and having multiple models and bidirectional transformations, but this is Lambda Days, so I won't. Instead, I'll go on and talk about what good programs are. So these are the criteria from the opening chapter of the book, and the first two are the important ones, I think, here. So good programs do what they're supposed to do. Okay, they're correct. There's some idea of what the program is supposed to do, and if it doesn't do that, then it's buggy and you'd better fix it. But in order to handle the fact that the information about, for example, what a program must do and about the environment in which it must do it will change, it's really important that programs should be clearly written, because otherwise we haven't got a hope of being able to change it in future and be able to keep it correct. You often, especially I have to say in the context of functional programming languages, hear people talk as though an important criterion is that good programs are concise. Okay, people will compare solutions and sometimes even solution languages on the basis of how few lines you can produce a solution in. And in the context of student programming courses, one can't avoid the idea that good programs get high marks, but that need not detain us here. And of course, there are many other criteria that sometimes matter, and again, we don't really need to worry about those too much right now. So in thinking about what I was going to talk about today, of course I have a bit of a problem, because I'm not going to sit here and talk to you as though you are students on first-year programming courses about what it takes to write good programming languages, because you're not, by and large, students on first-year programming courses, and you probably know a lot more than I do in many cases about how to write good programs in functional languages. So what I'm going to do is I'm going to put up the contents page of the book and say this is the kind of thing that I think we should be teaching our students, and students find it helpful to know about. I will point out a few things, and then I'll go and talk a little bit more about whether a language matters, and if so, how. So students need to be able to understand a bit about their language, of course. They need to know how to use the best tools and how to select tools. A thing that often gets forgotten is that beginning students can often have unpleasant disaster scenarios involving losing their programs. They need to be taught how to test their programs, including the very basic manual testing. And so on and so on. There's all kinds of skills about debugging and how to ask for help, how to improve people's programs, and how to, of course, do the mercenary stuff like scoring well in coursework and exams, and so on. So anyway, all of that's in the book, and I'm not going to say much more about it. What I'm going to go on and do is to talk a bit more about specifically functional programming. Well, does it matter? Does it matter what language we write our good programs in? You might expect me at this point to say, well, actually no, not as much as people often think, because I have emphasised the fact that many of the important skills in writing good programs are transferable between languages, and indeed they are. In fact, it's remarkably difficult to tell. If you want a reliable answer to the question, does it matter which programming language we write in? There's not a whole lot in terms of convincing evidence. And this paper that I'm citing here is a lovely rant on the subject, which you should read if you're interested in it. You should possibly also read Jeremy Gibbon's review of the paper, which you'll also easily come across. But I like this paragraph from it. So given the substantial economic investment in software and its importance to all aspects of society, one would expect the industry to use rigorous empirical methodologies to ascertain whether the benefits of eliminating or modifying programming languages or introducing new ones outweigh the disadvantages. Well, maybe. I think, however, if you would expect that, you probably would also expect modern medicine to be evidence-based too, and unfortunately, if you think that, I kind of have a bridge to sell you. because actually, although there are little islands of lovely randomized controlled trials and meta-reviews and what have you in medicine, actually most medicine is done on the basis of this is how it's always been done, and consult your own physician, because your own physician will have their own opinion based on their own experience, and it's not actually so very different from our world, unfortunately. But in fact, programming language selection, evidence-based programming language design, evidence-based programming language selection, is even harder than that. Why? Because you can't really do randomized controlled trials of most of the things we would like to have solid evidence about. You can only randomize programmers to different languages if they have very little investment in programming at all. For example, they're beginning students, in which case they're really not typical of the people you want to be studying anyway. And indeed, they have to have very little investment in the situation. So you would like to take a large sample of real programming projects in real companies that matter to the company's bottom line and try them out in multiple versions using different programming languages and see which one gets done faster and cheaper and with fewer bugs. And of course you can't do that. It's not ever acceptable. And so what people do instead, and this is very understandable because it's what's possible to do, is they do things like they study, well, what languages do people choose if they're taking part in programming contests where you have a free choice of language, or they look at, well, what happens if we look at systems in GitHub, say, and we look at what languages they happen to use, and we compare them on the basis that other things are equal. And the thing is, other things are not equal. Correlation is not causation. So you cannot assume that because a system came out being a good program and it was in language X, that shows that if this other system had been written in language X, it would have been good. It just doesn't work like that. So evidence-based programming language selection is far behind evidence-based medicine, and this is not just because people haven't invested in it. There are good reasons for that. Okay, so the question, which programming language should I use, is less like which COVID-19 vaccine works best, though heaven knows that's a hard enough question to answer, and at the moment we don't have an answer to that question, right? Because we haven't had head-to-head trials of the different vaccines, and the different trials that there have been of the individual vaccines have been done under different conditions, okay? So that's hard enough. But actually it's more like, what should I eat? Or which animal is best adapted for life on the savannah? Where, to be honest, one's first reaction to these questions is, well, that's a silly question, isn't it? Because it depends what you mean, okay? And that's really the situation here. However, this is not to say that evidence isn't useful and that there shouldn't be more of it, and there have been various attempts over the years to come up with sensible evidence about these things. And here are a few of the URLs and other sources that you can perhaps look for more information. So the top page, the Quorum Language Evidence page, Quorum Language is an interesting attempt at being evidence-based language design. So there's a bunch of people involved in that. Andreas Stefik is one of them. Programmingusability.org it seems to have come out of a special interest group held at CHI 2016, and unfortunately the content of the page didn't seem to go very far after that. But I think it's fair to say that one outcome seems to have been that Dargstuhl that took place in 2018, and that has an outcome which is well worth reading, with some interesting references to into the literature and reports of what sound like some very interesting discussions on the subject. The Psychology of Programming the Psychology of Programming interest group is at that URL, but unfortunately seems to have less than you might perhaps expect on programming language design and selection. The most interesting, very recent thing that I came across was this PhD thesis by a guy called Michael J. Koblenz, which attempts to use user-centered design approaches to designing programming languages. Now that's a very interesting undertaking. One of the things that struck me having a quick look at that thesis is the observation that the participants in the user-centered design often came up with unsound suggestions about what the programming language should do. And that unfortunately points out another difficulty and another reason why we have our programming languages are not really designed with evidence of what suits programmers in mind, it's because it's a very highly constrained problem. It's very easy for the programmer to say, it would be better if the language did this in this particular case, and for you then to find out that unfortunately it's impossible, either impossible in principle or undesirable for other reasons, to change the language so that it works in that way in that particular case, because it has to be possible to make it work in all cases, and possible to make it, do compilation and type inference and all these other things in a sensible way. And it's a hard problem. And so inevitably we fall back on anecdotes, and this gives me an excuse to tell some anecdotes about my own experience programming. So I'm kind of old, and so my first experience with programming was with a programmable calculator. But my first serious programming experience was in BASIC. I landed in an organisation which had better be nameless, where I was actually employed as a data entry clerk. But it turned out that I was sitting next to the computer manager. And his story was that he was the computer manager because decades earlier his desk had been next to the computer when the computer arrived. And he'd been quite interested, so he ended up as the computer manager. And it turned out that this organisation's business was entirely run by a suite of basic programs, which were there, accessible to me in source form on the computer I had access to. And I was able to decide that I didn't quite like how they worked and to edit them. And my nice colleagues in this place where I was temping were quite happy for me to do it, it turned out, because they were irritated by some of the things that the programs did too. And so I had a lovely time for a few months, sometimes doing data entry, and other times changing the functionality of the core programs that ran this organisation's business. I had absolutely no experience or training in programming or software engineering of any kind at that time, and I learnt all kinds of interesting things. So, for example, I learnt about the importance of testing. I learnt about that by changing the program that printed the organisation's checks, and accidentally changing it so that the next print run, all the checks came out with the date of 1st of January 1970. And although this was a long time ago, it wasn't that long ago. And then it turned out that each of the checks had to be hand cancelled, and its cancellation recorded in a big leather-bound book and signed by the organisation's accountant. I was not popular that day, and after that I had some idea about why testing was important. And there are more stories I could tell, but I think that one will do. Oh yes, the other one is security. The way it worked was that if you entered a password into one of these systems and you got it wrong, your wrong attempt was recorded in plain text in a file on the system. And you really don't have to see that many mistypings of banana to work out that the password is banana. Anyway, that was that. That was a very interesting experience and a first exposure to languages and to software engineering. My next two experiences were a very interesting contrasting pair. So as part of my PhD in pure maths, it turned out that I needed to write a program to solve some mathematical problem. And I did it in C, and I taught myself C from the venerable book by Kernighan and Ritchie. And that's a very good example of how not to learn to write good programs. It's a lovely, lovely book, but it's not a book that teaches you how to write high-quality programs that will be highly maintainable and so on. But then, when I went on to become a professional developer, I had to learn C++, and I did that from Russell Winder's book, Developing C++ Software, and that is, to this day, one of my favourite books about programming languages at all. Russell Winder very sadly died recently, which is a great loss to the community, but I strongly recommend that book because it talks a lot about how to structure your programs and how to make them good in all kinds of ways. And then I went on for a few years as a professional developer, writing in whatever I had to write in at the time, and those were a few of my favourite languages. And then I came back into academia to work on the Edinburgh Concurrency Workbench, which was by then a legacy system written in standard ML. And so I had to learn standard ML, which was my first serious exposure to functional programming. That was a very interesting experience. The most striking aspect of which was the incredible powerfulness of the type system. My colleagues sometimes used to say that once you'd managed to get your standard ML program past the compiler, past the type checker, there was no need to test it because it was certainly correct. Now, of course, that wasn't really true, but it was close enough to true to be pretty impressive to me at the time. But the corresponding frustration was that, as many of you will know, standard ML has a very powerful type inference mechanism, and so you don't have to give a lot of information about what the types of the things in your program are, and certainly in that context the convention was that one didn't. And so I repeatedly had the experience, as I tried to get to grips with this very complex program and to understand what it was doing, that I would say to myself, the compiler knows perfectly well what the type of this thing is, but it won't tell me. There's no easy way for me to find out. And that was incredibly frustrating. Around that time, and partly for that reason, I gave a talk to the Edinburgh ML Club entitled Why I Hate ML. You'll have learnt about me by now that I sometimes like to court controversy. And shortly after that, the group in Glasgow at that time that was working on Haskell got wind of this, about how I'd given this Why I Hate ML talk, and decided to invite me to give a talk to them, I think in the hope that they could tell me that I should be using Haskell instead. Unfortunately, most of the things that I hated about ML were equally true of Haskell at that time. Although certainly modern Haskell does a much better job of putting type information down in ways which are useful to programmers, so there is that at least. And since then I've been an academic, and as is the way of academics, I have programmed in the languages I have to teach, and those are some of them. That was a bunch of anecdotes, and it's not really evidence, but I mentioned earlier on the analogy with the question of which animal is best adapted for life on the savannah, and that might lead you to think about analogies with evolution by natural selection, and I think that's not a bad direction to be thinking in. So here are the situation characteristics that, as Darwin explained, enable evolution by natural selection. There has to be a collection of individuals which vary in some way. Some are more adapted and some are less adapted to particular ecological niches. There has to be some notion of replication with inheritance, inheritance enabling characteristics to be passed down from one generation to another, but somewhat modified in the process. And there has to be some kind of struggle for existence. If all individuals survive in every generation, then there is no evolution by natural selection, because there is no selection. And I think it's reasonable to say that if you take as your individuals programming languages, we actually have these characteristics as well. Some languages are better adapted than others for particular environmental niches. Languages descend from one another, if only by the designers of the languages having experience in previous languages, and so characteristics are passed down through the generations, sometimes with variations. And there is a shortage of, not of food in this case, but of attention from programmers who would be putting effort into learning the languages. And so I think we see an ecosystem of languages which is reasonably comparable to ecosystems of individuals of different species. We have specialist languages and generalist languages. Although we have to be careful to avoid the teleological fallacy, we do have some kind of notion of increasing complexity. We observe, I think it's reasonable to say, that things that turn out to be good solutions, good ways of handling particular characteristics of the environment, tend to spread among organisms and be adopted as standard ways of doing things. So here are a few examples of things I want to claim that we now understand, ways in which the ecosystem of programming languages have changed over the decades since programming was invented. If there's one thing that I think you should take away as part of what it means to write good programs, and help other people to understand as well when you have influence over them, it's that names matter a lot. the choices that you make about what to call the identifiers in your program of any kind have a huge amount of influence on how easy or difficult you later on or other people will find it to understand what your program does and how to change it. And it's not only a question of, well, here are the things in my program, now what is a good name for these for this thing. It's more interesting than that, because on the occasions when you find that you cannot think of a good, short, truly descriptive name for a thing in your program, that's quite often an indication, a clue, that the thing is not itself terribly well chosen. So, for example, if you're trying to say, oh dear, this function in my program can only be given a name which is rather long and complicated, often that's a clue that your function is trying to do several things at once, and that your program might well be improved by refactoring it so that you split your function into several parts, each of which can be given a good, short, descriptive name. And so it's possible to use the gradual improvement of names in your program as a driver for refactoring, for restructuring your program. That's a really useful thing to do. We know that structure matters. We know that encapsulation is good and spaghetti is bad. Why? Because as things change, as the requirements and the environments in which your program must operate changes, it is really helpful to be able to say, I don't yet know exactly what I have to change in my program, but I do know for sure that it's going to be something inside this 100-line section of my program, and it's not going to involve the millions of lines in the rest of the program. That's what encapsulation buys you. We all know what spaghetti code is, but I would love to know if anybody knows for sure with references what the origin of the phrase is, and I'll tell you for why. It's because it's possible that the origin is my father, who for some reason doesn't like to be described as the inventor of spaghetti code. He has a story coming from the probably early 1960s about how he had a discussion with C.B.B. Grindley, who was a programmer and author about programming at the time, about how one's code shouldn't be structured like spaghetti. And he says that he had to remembers that he had to explain that he wasn't talking about short lengths of spaghetti in tomato sauce in tins, which was the commonest way you would get spaghetti in England at that time, but rather about proper long spaghetti, the kind that came in packets or in an Italian restaurant. So I'd love to know whether he really did invent spaghetti code in that conversation, or whether there was an earlier reference or what. Types, I've said here, are a double-edged, very sharp sword. The question of whether static or dynamic typing is better, for example, for comprehensibility, is one of the few areas that's attracted most attention, in fact, in the evidence-based programming language design field, and you can find some descriptions of that in the URLs I gave earlier. I think it's reasonably uncontroversial these days to say that type information is useful in a program. I think, particularly in the context of functional languages, type-directed programming is a really interesting innovation, and you should definitely go to Edwin Brady's talk. He's going to talk about that, I imagine. And there's a bunch of stuff that we've also learned about process, most of which I've said already. But I don't want to only be uncontroversial in this talk. I like to be a bit controversial sometimes. So now let me go on and be really controversial, and perhaps I'm going to be quite glad that I'm giving this talk remotely at this point. I'm going to claim that for most people, most of the time, functional programming is worse than object-oriented programming. It's harder, and it's less useful. Well, how do we know? How can I claim such a thing? Well, fundamentally because it's less used. And you can have a bunch of different kinds of evidence about this, and you can argue about any particular piece of evidence. Here's Google Ngrams. They're great. They're lovely to misuse. And here is what happened to the phrases object-oriented programming and functional programming over the years. You see, they rose up together, but OO went much higher. Now OO's come back down again, which is kind of interesting, isn't it? You might say, oh, object-oriented programming was a flash in the pan, and now it's neck and neck with functional programming. I'm afraid I think that's probably not true. I think it's more that object-oriented programming is today known as programming, in the sense that it would be quite hard to get a generalist programming language that didn't have any form of objects adopted these days, but we could argue about that. You could also look at the TOB index, which doesn't have a functional language in the top few, or various other kinds of evidence. I'm afraid, I think, the fact is functional programming has not taken over the world, and object orientation has. And we could ask why and for whom, and does it matter, and will it change? Full disclosure, I'm not going to answer all those questions here, but I'm hoping to leave plenty of time for questions, and perhaps we can talk about it later. But before we can discuss it at all, we need to be aware at least of a controversy here about what functional programming is anyway. When we say it's functional programming, do we focus on what we want there to be, for example first-class functions? Do we say it's functional programming, it's a functional programming language if it has first-class functions? Or do we focus on what we don't want there to be, for example mutable state? Do we only say it's a functional programming language if it doesn't have mutable state? If you want one, then you can in fact argue that functional programming is a success, because, for example, there are now functional programming features in Java. People have demanded them, and there they are. And the same is true in many of the other popular languages. Some of the features that used to exist only in functional programming languages now exist in languages that are multi-paradigm, where you can also write imperative programs or object-oriented programs. So how bad is it if we have to settle for languages in which people can write functionally, but they can also write in other paradigms? Well, this depends on what your opinion of parsimony is, and here's a scale of different approaches. So one of my favourite languages is Perl, in which the motto is there's more than one way to do it. So this is the parsimony considered harmful end of the spectrum. This is the libertarian view that says it's not the language designer's job to impose a particular way of doing things on the programmer. And Perl's successor Raku is one of the examples of a generalist language which now has functional features. Later, Perl aficionados conceded that sometimes consistency is not a bad thing either. So the first motto there is abbreviated to Tim Toady, and the second, slightly less clearly, is abbreviated to Tim Toady bicarbonate. There you go. A step further is this item from the Zen of Python, where the idea, by contrast, is that there should be one, and preferably only one, obvious way to do it. So this is Python distinguishing itself from Perl, and it's been very successful in doing so, and in usurping the place that Perl used to occupy and taking over the world. Another way of thinking about this is this epigram from Perl's. A language that doesn't affect the way you think about programming is not worth knowing. This is the opposite end of the spectrum from the libertarian view, because it's basically saying the language should influence how you do things. You shouldn't just come in saying, I want to do it this way, and I expect the language to let me do it that way. If you somehow want to square this circle, one of the things you might say is, we can use functional programming for designing domain-specific languages, or indeed we can design domain-specific functional languages. I don't know how many people here have come across kernel F, the functional language within the MPS language engineering workbench, but that's quite an interesting thing to look at. Okay. But going on into being a little bit controversial in the last few minutes, I'm going to come back to conciseness a bit. So here's I had to have an example of a clever bit of Haskell in the talk. Here's a clever bit of Haskell. Be quick, what does it do? Now, if you're a clever Haskell person, you can probably work out what this does, and you may even get a bit of a dopamine hit from doing so. Functional programmers are a very clever bunch, right? Now, nothing wrong with being clever, but there is something about the community, right, where it's very invested in being clever, and cleverness being a characteristic of being a functional programmer, and I think that has quite a lot of implications, both for the community and for the success of functional programming. Because being clever's not necessarily always a good thing, and fundamentally the reason why is this, that debugging is twice as hard as writing the code in the first place. If you write the code as cleverly as possible, you are by definition not smart enough to debug it. And this is the kind of thing that goes through the minds of people who get faced with clever Haskell code, like what was on the previous slide, even if somebody got a nice dopamine hit from writing it that way, and somebody else might do so on decoding it, that's not so welcome if you're trying to make a change to it quickly. Especially when you realise that you could write it this way in an only very slightly longer version, which I'm going to claim is much quicker and easier to understand. It does exactly the same as the previous example. I've replaced fizz by dog and buzz by cat in the example because everybody knows what a fizz-buzz program is, and so if I had left it as fizz and buzz, that would have been too big a clue on the first example. So, I'm not going to say any more about how to write good functional programs. You should use good names, you should use a good structure, you should remember that there's no tax on keystrokes, and beyond that I'm sure you all know those things, and you know many more things than I do about how to write good functional programs. So let me just say one slide's worth of stuff about how to make functional programming succeed. So one way we've already mentioned is to inveigle functional features into other languages so that it quietly takes over the world. And the other way, of course, is to say, well, we can occupy important niches, either that way or by saying, well, there are these specialist functional languages which are good for particular things. Concurrency is perhaps the obvious niche these days. Data science is arguably another one, and you should definitely go to Kathy Fisler's talk, where I believe she's going to talk about that. If you want people to use specialist functional languages, then I'm afraid the big boring thing that absolutely must be done is tackling accidental complexity. So stuff that is not very interesting to programming experts or programming language experts, stuff like how fast the language changes and how difficult it is to install, and whether there's a debugger, and how good the compiler error messages are, and whether the documentation is up to date. And all of this kind of stuff, which is very difficult to do in the setting of an underfunded or a university or group where people are more focused on research and new features, but is absolutely crucial for adoption of languages. It has to be fun. Somebody has to find it fun, otherwise they're not going to put effort into it. But at the same time, I think you have to remember that most people, really honestly, do not much like programming, including most programmers, and that's fine. Most people just want to get the job done. Sometimes hard to believe, but true. Anyway, that's me. That's all I have to say. I hope I've left plenty of time for questions now, and that's my book, just to remember. On to questions.
Thank you so much. This was really engaging. Thanks. We have lots of questions in the Q&A tab. May I ask the authors of the questions to raise your hand? There is a button on the right hand side so that I can invite you on the stage, and this way you can ask the question yourself. We have Juan first joining us on the stage.
Hello. Hello, how are you? Yes, I was wondering what do you think about Scala? Because some people consider an hybrid language. Even Martin Ortesky itself, he claimed that he designed the language in that sense, having both paradigm, functional and object-oriented.
So I have never programmed in anger in Scala myself. I've written, less than a couple of hundred lines of Scala probably ever. So I don't really have a considered opinion. I mean, like you, I've heard people talk about it, and people seem to think it's an interesting language and certainly a very interesting undertaking to combine the paradigms in that way, but sometimes to find it a bit frustrating in the sense that the compromises necessary to fit functional features into something that had to work on the JVM sometimes irk people a bit. I can't really say any more than that.
Okay, thank you.
Okay, Manuel.
Hi. So I was wondering, this cleverness problem that you described, I think that's a really important problem. So I'm very happy that you talked about that. It's maybe one of the biggest problems.
Sorry, you're breaking up.
Sorry. So this cleverness problem, can you hear me right again?
Yes,
right.
Just about, yes.
Yeah.
And I can see your question in the Q&A, so that helps, yes.
Okay, all right. Yeah, so my question is basically, do you think is this a problem that is present in the community? Do just Haskellers think they must be clever and they are clever, and they say, well, everybody who isn't clever is not part of the community? Or is Haskell in itself intrinsically hard to learn that you have to, yeah.
I don't know.
Clever.
I mean, all of our first year students at Edinburgh learn Haskell, and most of them pass. So certainly at a basic level. I mean, that said, our students at Edinburgh are clever people. I mean, they have to have high level qualifications in maths to enter at all. So I think it's probably mostly a cultural thing. Maybe the sense in which it's influenced by the language is that because it's such a research active language, so I've said before, that Haskell changes fast and been corrected and been told, no, the language itself doesn't change fast, but sometimes, the environmental stuff and the libraries and what have you change. And that maybe is difficult to keep up with if you're not actually a programming language focused person in the first place. So maybe that contributes a bit. Monads are perhaps not as hard as people sometimes make out, but they're not that easy compared to, writing the same kind of functionality in Python. So maybe that's a thing you could point at that is a fact about the language as well. So yeah, I mean, I'm on the fence about this, as you can tell. I think it's, it's 6 of one and half a dozen of the other.
Okay, thanks.
Thanks.
Thank you. We have now Camilla as well, having a question for you.
Mm-hmm.
Let's see. Okay, there I am. I was wondering, who do you think are the most right about, or who has the answer of what a good program is? Developers with decades of experience, or academics with decades of experience, or do you have to be somewhere in between?
I think the people who write the best programs are the people who care most about making their programs good.
Okay. Do you think you can care too much?
Sorry?
Do you think you can care too much?
Oh, certainly. Yes. I mean, it certainly is possible to kind of suffer paralysis by never finishing your program because you're always kind of trying to rewrite it in the most elegant possible way. I've seen that behavior. I have seen it in both places, actually. I've seen that behavior more often in academics than in industry. I don't have a representative sample in either place, and I've seen good and bad programs written by people working in industry and by people working in academia. I'd have to say, if I were going to, suppose I were going to be forced to spend the next year of my life maintaining a program, and it could either be a program selected randomly from people working in industry with decades of experience, or selected randomly from people with decades of experience working in academia.
That's a good.
I would prefer to be maintaining the program that was written by somebody with decades of experience working in industry, personally.
Okay. Yeah. Yeah, I think that answers my question. Thank you.
Thanks.
Yeah.
Thank you. Very good one. Another one from Georgie.
Hi, can you hear me?
Yes.
Okay, so my name is Kroil for short. Right, hi.
I can't hear you.
So you can't hear me? Can you hear me?
I think I can hear you, so try to ask the question.
Okay, so the question is that it seems that most programming languages aspire to be as generic as possible. And then there are certain rules as like code, domain-driven design, and such things that tell you how to write good programs in such languages. So how does that reflect on programming languages, and also how strict would you follow such rule sets?
I'm not really a fan of following a strict rule set. Sometimes it can be useful, particularly for beginners, to present them with a sort of more or less formulaic approach to writing a good program, and to try to make sure that they don't forget a crucial step. And I've noticed that Felicen et al.'s book, How to Design Programs, has got several mentions at this conference already, and I know that's one of the selling points there. So I certainly think that it can help beginners. I'm not really a fan of it as being a thing that should be sort of promoted as a religion, with people saying you should always do it this way. The closest I come to adhering to such a religion would be that I think test-driven design is probably quite a good thing. I think writing tests before you write the code that it's going to test often helps. But even there, I don't always do it myself, and I don't think I would want to advocate that anybody should do it absolutely always without exception. So I guess the answer is actually I'm not really that big a fan of strict rule sets. What I'm a fan of is people mindfully thinking about what they're doing and working out for themselves, bearing in mind the situation they're in, what the right way to do it is in a flexible way.
Thank you.
I'm doing a lot of fence sitting this afternoon, aren't I? Sorry about it.
Thank you. That was a good one. We now have Philip.
Hello.
Hello, Phil.
So thanks for that nice talk, Perdita. You should have mentioned it to my class
Thank
that you teach in.
Yeah, it's cool stuff that I teach in.
I was also very sad that you pointed people at Edwin's talk, but not at my talk. They're both going to be about dependent types, I expect.
Oh, I'm sorry, I didn't even spot yours. Sorry, that
was Keynote
not
on Friday, I think. But the main thing I wanted to talk to you about was the slander that you uttered against monads.
Ooh.
So you claim, oh, well, obviously it's much easier to do it without monads. But I think that's just familiarity. So I wanted to put a challenge to you, right? Certainly many more people do it that way. Certainly many more people are familiar with doing it that way. But none of that is evidence that it's actually easier.
Oh.
So I was going to ask you, do you have any evidence that it's easier?
Well, how about the evidence that you don't teach monads compulsorily in your course?
Oh, that's because monads are about side effects, and side effects are hard.
I think a language in which side effects are hard has problems.
No, side effects are hard in every language.
Somehow people don't seem to find them hard in Java.
That's fair. Okay, so your evidence is even in a class where you've got somebody quite familiar with monads teaching it, they find it difficult to convey to students in the way that the students will find absolutely easy. That's an interesting challenge. Thank you for setting it.
I look forward to seeing how you meet it.
So do I.
Excellent. Thanks so much for the question and the interaction. We now have John.
Okay. I see myself there, so I'm on stage. Good. So I wanted to ask you about abstraction. Abstraction is one of our most powerful tools. But if you overuse it, it can make code incomprehensible. I would say that monads, for example, are a very good abstraction because they have so very many useful instances. But I wondered whether you have principles in general for deciding how much you should abstract. Where should you abstract and where should you not?
Ooh. I think I'm going to go back to Kent Beck and say you ain't going to need it. I think the point at which you should add an abstraction is when your answer to that is, yeah, actually, I am going to need it. So roughly kind of, I think the rule of three is not bad. If you are going to have 3 instances of your abstraction, 3 different uses of your abstraction, then most of the time that's going to be enough to make the abstraction pay its way. If you're only going to have 2, then actually quite often code duplication is better. Not least because when you've only got 2, I'm generalizing, of course, and it's always dangerous to generalize, certainly on the fly. But I think if you've only got 2 instances of the thing you're thinking about making an abstraction of, quite often it turns out that you're wrong in thinking that they have a common generalization. Quite often they just look as though they're the same at the moment, and the abstraction you would write isn't quite right at this point. And if you only have 1 right now, but you feel as though there must be going to be more in the future, you're very often wrong. And so I think I'm a fan of only abstracting once the work you're putting into making the abstraction is going to pay off right now.
Thank you.
Thank you, John. We have Bastian with his question as well. trying to hand the mic. Okay.
Hi, can you hear me? All right, thank you for the excellent talk. Well, maybe I can even, there we go. So I've written programs both in industry and in academia. And my experience is in academia, you're usually working by yourself. And so programming is mostly an engineering problem. And once you move into industry, it's suddenly it's a social and cultural problem.
Absolutely, yes. Although sometimes it's that in academia as well, actually. But
yes, it is.
Sometimes in academia it's a harder social and cultural problem because you're working with people who are not so invested in making the system work, and sometimes are only investing a small amount of their effort or move on much faster. So there is that. But yes, generally speaking, I'm sure you're right. Yeah.
Yes, and so sometimes in industry, I wish for programming languages that are stricter and make it easier to achieve some conformity in larger groups. Do you have thoughts on that? Like, it's easier to be consistent across a Haskell code base with 10 people than across, let's say, a Python code base.
Yes.
And
so
sometimes the technology helps along with the cultural aspects.
So what kind of consistency are you mostly thinking about there?
Well, in this example, I'm probably mostly talking about like safety and side effects that are easier to control along larger groups with.
So it's a type system mostly that's helping you there. Yes. Yeah, I'm with you. Agree. And there's a sense in which the present day situation where people write large systems in Python or in any other dynamically typed language seem to me like maybe a bit of a mistake. I'm tempted to go out on a limb and say actually any large system, any long-lived system, any large system in terms of a number of people involved really ought to have a type system, and perhaps really quite a strong type system in order to keep it in order.
Or at least some immutability.
Yeah, I think so.
I think there's more dynamic systems that focus on immutability that still get a lot of the value proposition that we have in FP languages.
I mean, I'm hesitant because I don't have the experience to back up my opinion there. I've not been involved in maintenance of a large Python system, but it does slightly horrify me. I do this kind of thing.
All right, thank you very much.
Thank you.
Our time is up, but it was such an excellent section. Thank you so much for addressing most of the questions. There is quite a few more in the Q&A tab. So after a short break, I hope that you can sit at one of our tables and the audience can join you and continue the questions and discussions at the table.
Well, thank you very much for all the excellent questions, and thank you again for the invitation. I will go and refill my coffee, and then I'll come back and sit down at a table, as you suggested.